In this lecture, I will introduce a new phenomenon, electricity. I will explain the nature of electricity, where it comes from, the basic electric charges that carry electricity, and the force that governs the interaction between individual charges or charged objects. For some perspective, first I want to give some historical account of how the knowledge about electricity has evolved over the time. The early Greeks knew that amber, which is a fossilized tree sap currently used in jewelry, had the interesting ability to attract bits of fiber and hair after it was rubbed with some fur. This was one way of recognizing an object that was electrified. And in modern terminology, we say that the object is charged. This doesn't explain what charge is, but it's a nice way of referring to this condition. In 1600, English scientist William Gilbert published a pioneering work in which he pointed out that this electrical effect was not an isolated property of amber, but a much more general property of matter. Materials such as gems, glass, and sealing wax could also be charged. Rubbing together two objects made from different materials was the most common way of charging an object. In fact, both objects became charged. And after Gilbert, many experimenters joined the activity of investigating electricity. But the question of what happens when an object gains or loses this electrical property remained unanswered. In an effort to explain electricity, Gilbert proposed the existence of an electric fluid in certain types of objects. He suggested that rubbing an object removed some of this fluid, leaving it in the region surrounding the object. Bits of paper were attracted to the object by the draft of the fluid, returning to the object. Although many other electrical phenomena could not be explained with this idea, it was the beginning of attempts to model the underlying invisible process that caused the electrical effects. Very little progress was made for almost 130 years, until in 1730 it was shown that charge from one object can be transferred to a distant object if metal wires connected those two objects, but not if silk threads were used to connect the objects. And so with this emerged the notion of conductors and insulators. Conductors are materials that conduct electricity easy. Typical materials that conduct electricity are most metals, and electrical wires are made from metal, for example, copper, gold, silver, platinum, aluminum. As you can see here in the list of conducting materials, we have 4 different metals shown, and then we also have a liquid, and that is seawater. Seawater is a conductor of electricity because it has a structure of positive and negative ions which can move inside the volume and thus conduct electricity. Water or seawater is not the only liquid that can carry electrical charges. In general, liquids that dissociate into positive and negative ions are good conductors. Other examples of liquids that are good conductors are acids and bases. A specific type of conductor of electricity, which is very important for us, is the human body. The human body consists of almost 80% water, and since we have a good balance of salts in our body, that water is actually can dissociate into positive and negative ions, and therefore it's a good conductor of electricity. The importance of this fact for us is that if very high dose of electricity passes through a human body, it is fatal for a human. The second class of materials is electrical insulators. So insulators are materials that do not conduct electricity. So examples for such materials are rubber, glass, oil, diamond, dry wood, and of course plastics. So these materials do not conduct electricity. Let's discuss several factors that affect electricity. We already know that liquids, and more specifically water, conduct electricity. So it's no surprise that humidity can affect the electric charge on charged objects. So humidity affects the amount of electric charge in a conductor. The amount of electric charge that an object contains can be reduced by the humidity in air. When the humidity is high, for example in spring and summer, charge can be conducted away by the moisture in the air. And when the humidity is low, for example in the fall and winter, charge is not being conducted away as easy or at all. So this is the reason for getting shocked when touching an object that is charged or can be charged in the cold months, and not doing so in the warm months. And we know very well that when putting on clothes that are made from synthetic fibers, in the cold months, you hear that crackling as you put in the clothes on. And then if you touch a doorknob or another object that can be charged, very often we get shocked. In the warm months, because of the high humidity, that does not happen, because the humidity takes away the electricity or the excess electrical charge from the surfaces of objects. Grounding is another mechanism of affecting the amount of charge on an object. Grounding is the process of connecting a charged object to the ground. The ground is an infinite reservoir of charge available to move around. The ground of the earth is made from all kinds of materials mixed together. There is a lot of conductive substances that are mixed in the soil of the earth. And as such, there's essentially an infinite amount of charge available to move into ground or from ground into an object. So grounding an object with excess charge on it will cause charge to flow from or to ground to balance the charge on the object. This process works with conductors only. So to ensure accidental grounding is avoided, conductors are insulated from the surrounding with an insulating material such as rubber or plastics or ceramics, and so on. And the most common example of such insulation is a regular household circuit wire. Of course, also the wires that are used in appliances to connect to the power grid. So here's an example of how grounding works. Here we have a charged object which has an excess of one type of charge and much smaller number of another type of charge on it. So the ground is an infinite reservoir of charges. So that means that it has infinite amount of the one type of charge and also an infinite amount of the other type of charge. So then if I connect the object with a wire to ground, since I have excess charge of one kind into the object, that means that this excess charge will be attracted to move towards ground, like so, until I end up with the following situation. I will end up with having the same number of charges of each kind in the object. In the ground, we still have an infinite amount of each type of charge. And because we have a balance of charges in the object, there is no longer flow of charge through the wire towards ground. You can also consider the other possibility where we have, again, an imbalance of charges in the object, but we have more of this type of charge than this type of charge. So then what will happen is we're going to get a flow of charge when we connect the object to ground with the wire, but this flow then will be from ground up towards the object, and it's going to continue until a balance of charges is achieved in the object. So this is the basic principle of grounding. And so I mentioned that the human body is a very good conductor of electricity, and where the danger is with that is if somebody touches a source of a lot of charge, such as an object that's charged with an unbalanced charge, and ground at the same time. So you can think of the person essentially playing the role of the wire that connects the object to the ground. And so when that happens, if large enough amount of charge passes through the human body to ground, that is what damages the body and can be fatal for that person. As I already mentioned, conductors have been established to be materials that can carry electrical charges from one charged object to another. So that means that these electrical charges will move inside those conducting materials. And so we have a wire here. We know that electricity travels along the wire. For insulators, they do not conduct electricity, which means that electric charges are not going to travel inside rubber or glass or oil or diamond or wood. However, it is possible, and it's a common thing, to be able to deposit electrical charges on the surfaces of insulators. The difference from conductors is that these charges stay put where they were deposited. They do not migrate around or through the body of the insulator. So if you put a certain amount of charge on a piece of rubber, that amount of charge will be fixed at the places where it was deposited. If you put a certain amount of charge on a conducting wire, the charge will move in the wire until it reaches a place which was imbalanced, and balance is achieved. So the main reason for charges flowing in wires or metals in general is that because of imbalance between the ends of the wires. Now let's talk about electric charge and see what that is. I already mentioned that, but now let's make it official. Electricity is carried by electric charge. And experimentally, it was determined that there are only two kinds of charges in existence: positive charge and negative charge. Now let's look at the origin of charge to understand how electricity is carried by charges. Charge is a property that many elementary particles possess. The smallest amount of charge in existence is the charge of the electrons and protons. Electrons and protons are two of the particles that make up the atom. So here is the structure of an atom. Of course, this is idealized and it's called the planetary model of atom. In reality, that is not what it looks like, but the approximation is good enough for our purposes. So the atom consists of a nucleus, which contains two types of particles. One is positively charged and one is neutral. And then electrons that orbit around the nucleus, similarly to how the planets orbit around the sun, and thus the name, a planetary model of the atom. So in the planetary model of the atom, we have the protons, which are located in the nucleus, and they're positively charged. And then we have the electrons, which orbit around the nucleus, and they're negatively charged. Finally, we have the neutrons, which are electrically neutral, so they don't have any charge. They're also located in the nucleus. the charge of one proton is 1.6 times 10 to the negative 19 coulombs. And this charge is considered positive. The charge of an electron is 1.6 times 10 to the negative 19 coulombs. And this is considered negative. So by magnitude, the two particles have the same amount of charge, but for protons, we consider this to be a positive charge, and for electrons, we consider this to be negative charge. The unit for charge in the metric system is coulombs, named after the French physicist who was able to derive the relationship for the force between two charged objects. And so the electrons orbit around the nucleus and are held in orbit by the force of interaction with the positively charged nucleus. But not all electrons will be orbiting at the same distance from the nucleus. So for example, here I've shown two electrons that orbit along different orbits around the nucleus. But for metals, we have many more electrons that orbit around the nucleus. So we have electrons that are further and further away from the nucleus. So the further an electron is from the nucleus, the smaller the force between that electron and the nucleus becomes. And so when an electron is far enough from the nucleus, it is fairly easy for that electron to be taken away by way of a strong attractive force outside of the atom, or simply by friction. Remember at the beginning I was talking about charging objects by simply rubbing them together. So then a free electron will move between the atoms of that material and can be trapped by another atom that has electron deficit. But this free motion of electrons inside the material is how the electric charge is carried. So this applies for metals. When we talk about liquids such as acids, bases, or water, what happens is formation of positive and negative ions occurs, and then based on difference in charge in the volume of the liquid, these ions will move in a certain way, and that's how electricity is carried. So let's look at the structure of a metal conductor. So this is a wire, and we know from before that metals have a symmetric crystal structure. We call this crystal lattice. So here are the atoms of this metal nicely arranged symmetrically inside the volume of the metal. And so we know that each atom has a nucleus with a number of protons, and then a bunch of electrons orbit around the nucleus. When there is many electrons per atom, some electrons are going to be positioned way far away from the nucleus, and as I said before, the force of interaction between those electrons and the nucleus will be very weak, and so that makes it very easy for an electron to be swept away, or just to simply jump the atom. So let's say this electron here hops from this atom and starts to move randomly inside the volume of this wire. The same can happen to other electrons too. And so there is billions of atoms in the lattice of a metal wire. And so therefore, there is billions of electrons that move around in the volume of the wire. And so therefore, we have plenty of free charge that moves around in the volume of the wire. So if I'm able to create an imbalance of charge between the two ends of the wire, that is going to cause this free charge to move in a particular direction in the wire. This is the basics of electric circuits, which we will discuss in the next chapter. Let's summarize the knowledge we have so far about charges. Positively charged objects have excess positive charge on them. Negatively charged objects have excess negative charge on them. And finally, electrically neutral objects have equal amounts of positive and negative charges on them. So these objects are not completely devoid of charges. They just have equal numbers of each kind of charge on them, which balances out to produce a zero net charge. Experimentally, it was determined one very important property of charges, and that is that like charges repel and opposite charges attract. That's why it's possible to ground an object and achieve equilibrium of charges on a charged object, just like I showed in a previous slide. Let's do the following example. The nucleus of a certain atom contains 81 protons and 128 neutrons. What is the total charge of the nucleus? The total charge will be equal to the number of protons in the nucleus times the charge of one proton. So that is equal to 81 protons times the charge of one proton, which is 1.6 times 10 to the negative 19th coulombs, which gives us 1.3 times 10 to the negative 17 coulombs. The number of neutrons does not play a role in the calculation of the total charge of the nucleus because neutrons are electrically neutral, so they don't have charge. Let's do one more example. How many electrons does it take to have a total charge of negative 0.5 coulombs? So the number of electrons will be equal to the total charge divided by the charge of one electron. So this becomes minus 0.5 coulombs divided by the charge of one electron. So this is minus 1.6 times 10 to the negative 19th coulombs. Remember that the charge of an electron is 1.6 times 10 to the negative 19 coulombs with the negative sign because the electron is a negatively charged particle. So calculating this gives us 3.1 times 10 to the 18th electrons. Doing problems where a certain type of charge is in excess for a charged object, to calculate the total charge of the object is done in the same manner as those two examples. You simply need to determine which kind of particle is in excess and then multiply by the charge of a single particle, so either the charge of an electron or the charge of a proton, to get the total charge of the charged object. Another important property of electric charge is the concept of conservation of charge. So historically, just like Gilbert, Benjamin Franklin believed that electricity was a single fluid and that an excess of this fluid caused one kind of charge state or the other. Because he couldn't tell which charge was which, he just picked one kind to be positive and the other one to be negative. So for example, if you rub a glass rod on a piece of silk, the charge that's deposited on the rod is going to be a positive charge. And if you rub a piece of ebonite with some fur, the charge that is deposited on the ebonite will be a negative charge. The model that Benjamin Franklin suggested couldn't explain how charge was created or deposited on objects. However, one other suggestion from his model turned out to be valid, even though his model wasn't correct. And that suggestion was that the fluid that leaves the object or is received by the object is in constant equilibrium, which means that for any object that is charged and it is not in interaction with other objects, so in other words, it's isolated, the amount of charge on this object will be conserved. It will never change. And so the conservation of charge can be stated in a very simple formulation. The statement of conservation of charge principle states that in an isolated system, the total charge is conserved. This has important consequence when we look at induced attractions between charged objects. Consider a metal sphere which is neutrally charged, meaning it doesn't have either positive excess charge or negative excess charge. And this sphere is hanging from this thread, and this thread is non-conductive. So the fact that the sphere is neutral means that it has the same amount of positive and negative charges. Let's see what happens if I approach a charged glass rod. So the glass rod, as we already saw before, has positive charge deposit on its surface. And so let's take the rod and place it closer to the sphere. So placing the positively charged rod close to the sphere results in attraction between the sphere and the rod. But how is this possible if the sphere is neutrally charged? Well, the sphere is neutrally charged, which means it has equal number of positive and negative charges. But remember that the sphere is made out of metal. For example, aluminum or steel. So then what happens is the charge on the sphere is going to separate. Remember that like charges repel and opposite charges attract. So, since the sphere is made from metal, the positive charges on the sphere, which are in the nuclei of the atoms that make the sphere, cannot move. They are fixed in place. But the electrons in the metal can move. And so, the positively charged rod is going to attract many electrons towards the side of the sphere that's closest to the rod. And so overall, that side of the sphere will become negatively charged. And so because of that, the sphere is going to get attracted to the rod. But now, since more electrons are on the side that's closer to the rod, the opposite side of the sphere will be more positively charged. And so this is an example of an induced attraction where an object that is electrically neutral can actually be attracted to an object that has a certain type of charge on it. If this rod was negatively charged, what would happen would be all the electrons will be pushed away from that side of the sphere, and then the side of the sphere that's closer to the negatively charged rod will become more positively charged, and the opposite side of the sphere will become more negatively charged. But placing the two objects close to each other will result again in attraction between the two. And so this is what this example will look like. So this is all due to the properties of conductors and the ability of electric charges to move freely in conductors. As far as the rods are concerned, these are insulators, this being a glass rod and this being a plastic rod. So the charge that's deposited on the surfaces here remains fixed in place. It does not move. So to summarize, in conductors, the charges that move are electrons in metals. The protons are fixed in the nuclei, so they don't move. And then for liquids and gases, we have positive or negative ions.